Hi, NA Physics, it's Mr. Neff. Let's talk today about multi-lens systems and devices. And before we do, did you hear why the phone wore glasses? I'll tell you at the end of the video. So let's talk about a device first. And the first device we'll talk about today is a simple camera. So a simple camera is basically just a mechanical version of an eyeball. You see what it is here? There's an object that you want to take a photograph of right there, and the light off of it is going to hit this converging lens. Now this converging lens is, since the object is outside the focal point, we're going to get that real image, which is good. It's the only image that you could actually focus on the screen or get a picture of. So that image is going to be formed back here. Now what you're going to do to get a nice focused image is you're going to move the lens either forward a little bit or back a little bit. And now it turns out, because you're doing that, when you move it forward or move it back, you not only are you changing the DO, but simultaneously you're changing the DI. And so a little bit of movement makes a big difference in how focused the image is. And so it turns out you don't need very much movement to focus a picture. That's where maybe in your phone you don't even notice that the lens is moving at all. If you are able to move the lens a lot like this, then you can focus on lots of different things. And so, as I say, we don't necessarily have to have a lot of movement to get a great focus. You don't have to be like this guy. Now, a lot of times in devices, there's more than one lens. And so here I have two lenses together, and you can see that if you just look on the left, this is essentially what you're used to. You see an object outside the focal point of a converging lens. There are our three rays that we're used to seeing, and we're getting a real inverted image like we've seen a million times. Now, if you look at this through another lens, so here you are, the observer, looking at this candle on the far left, what's going to happen is the image from the first lens will become the object for the second lens. And so now I take that candle to be a second object. I understand that it's just a real image from a first object, but it is real, and so it can become a object for the second one. It turns out that it could still do that even if it were a virtual image. The image is going, the rays are going to come off, parallel, chief, focal. Now, don't misunderstand. See the path that this artist drew in pink. That's the parallel ray. That's the parallel ray again. What they're not saying is that there is a change in the path of the light right there at that candle, the second candle. There's nothing to make it refract right there, right? That's not an interface or anything like that. So there are a gajillion light rays converging there. We draw three of them, but there are tons and tons. There happens to be one that is moving parallel, and so they're just drawing that one too. They're not saying that that light was actually bent right there. But all it is to say that the object from the first lens becomes the image for the second lens, and we could do the same thing on this second picture. So how about an example of all of that? And so here I have two converging lenses that have the same focal length of 5 centimeters, and so there they are. They have a common principal axis, and they're separated by 22.6 centimeters. So distance there to there, 22.6 centimeters. So we have an object 10 centimeters to the left. Here it is over here, kind of like at 2F. Now you can remember 2F is a special point in terms of magnification. I'll bring that up at the end of this example. And it says, what's the image distance relative to the lens on the right of the final image produced by this two-lens system? Well, similar to that example that I just showed you, we could go ahead and draw in the parallel ray. We could draw in the focal ray. We could draw in the chief ray. And we're going to get an image formed right there. And then we could say, okay, well, based on that, now we could have a parallel ray. We could have a focal ray. And we could have a chief ray. And so this is the ultimate image, the second image, the one that you're really going to see if you're looking at this from the far right here. Okay, so they want to know how far is this distance right here. Okay, easy enough. Why don't we first figure out how far this distance is, this first DI. We can subtract from that 22.6 to get what this what the DO is for the second lens, and then we'll go from there. So you remember thin lens equation, 1 over f equals 1 over DO plus 1 over DI. And so it seems like I'm using this to solve for DI all the time. And so I can't tell you how many times I've done that algebra on it. So 1 over the focal length of 5 centimeters, this is converging, so it is positive, minus 1 over the DO, this is 10 centimeters. What do I have there? I have 2/10 minus 1/10, and that is 1/10. That's the 1 over the DI, and so DI itself looks like it's 10 centimeters. Okay, you knew that that was true too, because remember that whenever we're at that 2F point, or the radius of curvature, that was supposed to be the place where you went from a small magnification to a larger magnification. Right there, the magnification was, well, the object and the image were the same size. It was upside down, so the magnification was -1 right there. So if magnification is -1, remember magnification is negative DI over DO. So that says that the DO and the DI have to be the same size. All that is to say, I should have saw that 10 centimeters coming. Maybe you did see it coming. Then I'm going to do the same thing over here. So now this distance is 10 centimeters. So that means this distance right here is 22.6 minus 10, 12.6. Now that's going to be positive because it's still to the left of the lens 2. And so now this time I'll say 1 over DI is 1 over F minus 1 over DO, or 1 over 5 minus 1 over 12.6 centimeters. That's not as easy to do in your head, so I did that on my machine before I started the video, and I got 8.3 centimeters, which looks actually pretty good. This is a really crude sketch, but it looks pretty good. 8.3 centimeters right there. Now, they didn't ask this, but this person might say, what was the ultimate magnification of this? How big is this HI compared to this HO? Well, the magnification of a system is the product of the individual magnifications. And so magnification 1 times magnification 2. Magnification 1, we said, was -1. It was -1 because the object and the image were the same size on the originally, and it was -1 because we had the object at the 2F point, and it was -1 because the DO and the DI were the same size. Now, what about the magnification 2? Well, magnification 2 is the negative DI over DO for the object 2, lens 2, negative 8.3 centimeters by 12.6 centimeters. I did that before the video too, and I got negative 0.659. And so I'll multiply those together, and of course the math is easy, 0.659, but do you see that it comes out positive? And that said that even though in between we had an inverted image, and so we had a negative magnification just for the first lens, whenever you look at the whole system, the magnification is positive. It does give you a smaller image than what you started with, only 66%, but it is still upright. Before we leave, if we can just talk about 2 more optical instruments, let's talk about the microscope, which is a lot like that last example because it uses 2 converging lenses. So a compound microscope is going to be this combination of 2 converging lenses. You're going to have down at the bottom, down by the specimen, you're going to have an objective lens, and then up by your eyeball, you're going to have a lens called the eyepiece. And there it is. Now, what you're going to do whenever you're focusing that is you're going to try to make an image of the specimen. So here's a specimen down here that's going to be observed, and it's very, very small. Of course, that's the whole point behind a microscope. You're going to try to make a real image right there at the focal length of the eyepiece. And so whenever you're adjusting, you've done this before, you turn this knob right here, and that's going to move this eyepiece up or down depending on which way you're turning it. And you're going to try to make it so that the image from the objective lens is going to be right at the focal point of the eyepiece. Because if you do that, remember that that's whenever you get that object, that image, at infinity. And so that's nice because whenever the image is at infinity, then you can just, with a very relaxed eye, just stare straight ahead. So if you're focusing this microscope properly, you're going to be able to look in there all day. It's not going to give you any kind of eye strain or anything like that. It's going to be a very, very relaxed eye. And so that's that idea of a compound microscope, using the ability to change where the eyepiece is relative to the objective so that you can get the image from the objective at the focal point of the eyepiece. Now, similar to that is the telescope, the astronomical telescope especially. Now, the astronomical telescope is a similar thing. It also uses two converging lenses. But now with two converging lenses this time, you're going to make it so that the two focal points coincide so that you can get a ton of magnification. So look at this. So this picture is going to look primarily like the last one. So here's the distant object you're going to look at with the telescope, a star or the moon or something like that. And so here come the rays, and obviously we got to fit it on the screen, so we had to break that, but here those rays are continued here. Now, what's going to happen is, because this object is so far away, the image is going to be formed at infinity, you see. And so we're going to say that here's the image, the original image formed by the first object, by the objective lens, and it's formed at the objective lens's focal point. Now what you'll do is, to get tons of magnification, you can put the focal point of the eyepiece so that the first image that you formed is at the focal point of the eyepiece. And so if you do that, same thing as I said before about the microscope, you're going to get an image and it's going to be way out at infinity. So you're going to be able to look at it comfortably. You could look at this telescope all day and you're not going to have any eye strain with that at all. Your eye's going to be totally relaxed. And because you had the two focal points coinciding, you're getting tons and tons of magnification on that. And, speaking of lenses, before we go, did you hear that why the phone had to wear glasses? Well, it's because it lost all its contacts.